Something was wrong the moment the German engineer laid his palm on the Sherman's hull. He had expected jagged amateurish welding, evidence of a cheap mass-produced machine that could be fixed only in depots. Instead, his fingers passed over a seam so regular it could have come off an assembly line and been measured with a micrometer. The welds were uniform. The plates met with the quiet confidence of a product designed to be taken apart and put back together quickly, again and again. That single touch would set off weeks of examination that quietly, relentlessly undermined the myths German officers had long relied on. That American tanks were crude, expendable things made to be thrown away. That German engineering was inevitably superior. This was April 1943 at Kummersdorf. The tank on the yard had a desert dust film along its flanks and a nickname that would follow it through reports: War Daddy 2. It had been captured on February 22, 1943 in Tunisia and brought back for study. To many on the high command, the captured Sherman was evidence of a doctrine: quantity over quality, compromise over excellence. To a growing number of engineers and eventually to a stunned Albert Speer, it became evidence of something else, a philosophy baked into every design decision that favored one unavoidable truth of industrial war: a machine that runs reliably, can be repaired quickly, and can be produced in huge numbers will outlast a technically superior machine that cannot. If this kind of deep dive into machines and strategy appeals to you, subscribe for more history engineering investigations. The inspection began at the outside and worked inward, as if the tank were a patient on a forensic table. First came the armor. Measurements showed a frontal plate around 51 millimeters and sides about 38 millimeters, figures that, on paper, spoke to a middle road between protection and mobility. Those numbers alone meant little when set against the wider context of design intent. The Germans had expected sloppiness. Instead, they found thoughtfulness, armor that could be manufactured rapidly, hardened enough for the expected threats, and arranged to make routine maintenance possible. The welds were the first real surprise. Where some imagined American workshops pounding out rivets and rough joins, the engineers found clean, machine-made seams. Uniform beads ran in tight, even lines. This was not craftsmanship in the German sense, no hand-filed join or intricate fitting. But it was industrial craftsmanship, repeatable, reliable, and inexpensive at scale. It was the product of jigs, fixtures, and methods designed so dozens of semi-skilled workers could produce the same unit over and over with predictable results. In a war where loss rates climbed and replacement became a daily need, predictability mattered as much as ultimate strength. The engine bay told a louder story. Under the Sherman's rear hatch sat a Continental R975 radial engine, a piece of engineering that had its roots in aviation. Rated around 400 horsepower, it was an odd fit at first glance, an aircraft-derived power plant powering an armored vehicle. But the oddness vanished when the engineers opened the access panels. Large hatches and straightforward service points made routine maintenance and field repair feasible. Spark plugs could be reached without disassembling half the compartment. Oil and filter changes could be done quickly. The design prioritized getting crews back on the road with minimal tools and minimal delay. For German mechanics used to the compact, intricately packaged Maybach engines, this was revelatory. The Maybach was technically sophisticated, an engine that squeezed performance from tight spaces. But that sophistication came with costs and accessibility and field repair time. The American approach looked, functionally, like a deliberate compromise. Accept a bulkier, less glamorous engine in favor of rapid servicing and a higher likelihood the tank would be running tomorrow. A machine's usability in the field is a different metric than its nominal peak performance. An engine that produces more horsepower on a test stand means little if it is down for days with a broken pump that cannot be replaced. The Sherman's accessible layout translated into minutes of service, not hours, into a better chance that a unit could be patched and returned during a campaign, rather than waiting for rail transport and depot attention. From engine to transmission, the Germans kept cataloging differences that had strategic weight. The Sherman's powertrain hummed with an almost domestic steadiness when they ran it on the test bed. That hum, the technicians remarked, was not the metallic wail common in some German gearboxes. It was an engineered smoothness. Open the gearbox, and the teeth of the gears revealed another surprise: herringbone and helical patterns, rather than the simpler spur gears many expected. Herringbone gears are a refinement: two mirrored sets of helical teeth back to back, their opposing angles canceling out axial thrust and allowing for smoother engagement under load. Compared with straight-cut spur gears, they run quieter, transmit torque more evenly, and suffer less wear when properly machined and lubricated, but they are also harder to make. They demand more precision tooling and careful heat treatment. On a continent where high-grade tooling material and specialized cutters were increasingly scarce, the Germans had not made herringbone gears ubiquitous. For American production, however, the investment in these gears paid off by extending the life of the transmission under desert conditions. The numbers the Germans recorded told a stark tale. Transmissions and final drives on Panther tanks were notorious for short lifespans. On some accounts, certain German final drives averaged as little as roughly 100 miles before failure under operational strain. The Sherman's transmission assemblies, by contrast, were documented with lifespans approaching 3,000 miles in some service records. Those figures should be treated cautiously and in context. Terrain, crew practice, and operational tempo all affect wear. But the order of magnitude difference shaped the day-to-day reality of armored operations. A tank that needs a final drive rebuild every few weeks cannot sustain continuous action. A tank that can run thousands of miles between major overhauls changes the mathematical balance of availability. The practical implications of gear choice were visible in the maintenance shed as much as on paper. German technicians contrasted the Sherman's steady mechanical voice, a crisp, contained hum, with the Panther's shriek under strain, a sound that often prefaced gearbox trouble. Durability in the transmission meant fewer recovery operations, less heavy salvage, and fewer days out of action waiting for scarce spare parts. In a war where the front lines moved and the capacity to tow and rebuild tanks was limited, a design that reduced logistic strain had a force multiplier effect. The Germans' inspection did not stop at the drivetrain. Inside the turret they found a compact, efficient fire control arrangement, and tucked around the breech, a small but consequential piece of kit: a Westinghouse gun stabilizer operating in the vertical plane. It was not the elaborate two-axis stabilization the Germans had seen in some experimental forms, but it did something very practical. By reducing vertical movement of the gun as the tank moved, the stabilizer shortened the time required to bring the weapon to accurate fire after a maneuver. In the chaos of mobile battle, the ability to fire where you moved, rather than to stop, steady the hull and then aim, mattered for first-round hits. Precision gyros, small control boxes, and mechanical linkages on the Westinghouse unit were evidence that the Americans had given attention to what engineers call time to fire. It is a simple concept. In a duel, the one who can put the first accurate shot on target often determines the outcome. You can have the thickest armor and the best ballistics, but if your gun needs half a minute to become usable after moving while your opponent can fire in seconds, your technical edge is negated. The stabilizer was not a miracle device, but it was a pragmatic one, designed to increase the Sherman's combat effectiveness in the everyday moments that mattered. The Germans did not discover these elements in isolation. They tested, measured, and logged. They ran the Sherman over rough tracks, listened to bearings, timed maintenance tasks, and compared notes with field reports. All this quiet work came to a public head in a demonstration that would almost become a textbook example of how appearance and optics can mislead. At a sandy incline outside one of the proving grounds, recorded in some accounts as a hill climb demonstration, at a site variously transcribed in the primary record, verify, the German High Command arranged a staged contest. A Panther was run up the hill and, to the satisfaction of many onlookers, it climbed with apparent ease. The Sherman on the same slope slipped and failed to achieve the same triumph. Generals applauded what they took as confirmation. The Panther, with its sloped heavy armor and powerful drive, had superior climbing capability. The optics were undeniable in the moment. Photographs would show the Panther posed on the crest like a victory tableau. But the engineers who had been living with War Daddy II knew the fuller reality. The Sherman that had stalled on the hill had already traversed over 200 miles across the North African desert before it arrived at Kummersdorf. It had been run hard, repaired in the field, patched and serviced and pushed back into service repeatedly. The Panther might have conquered a single steep slope in a controlled test while fresh from the factory floor. But the Sherman's strength, its ability to keep going, day after day, under the unsympathetic harshness of wartime conditions, was less glamorous and less photogenic. The generals applauded a single technical feat. The engineers noted the record book. That difference, between a provocative demonstration and the grinding arithmetic of operations, was a fault line in German strategic thinking. An elegant performance on a test track did not automatically translate into sustained combat advantage when crews lacked spares, when maintenance units were overwhelmed, when supply lines were strained by Allied interdiction. Machines that demanded precision repairs or rare materials could be brilliant on a clean proving ground and useless on a muddy, bombed supply road. Word of the Kummersdorf findings moved upward. Albert Speer, Reich Minister of Armaments and Production, examined reports and the machine itself, not in theatrical fashion but as an administrator measuring consequences. What he saw underscored a dimension of modern war that transcended turret ring diameters and top speeds. Industrial capacity and design philosophy determined fighting power over time. A tank designed to be repaired quickly and produced in vast numbers presented a resilience that a technically advanced but delicate tank could not match when the logistics tail was cut. Speer's recognition was not a moral judgment about American engineering. It was a strategic arithmetic. The Allies' ability to churn out 49,324 Shermans, numbers taken from service records of production, against German outputs of roughly 6,000 Panthers and about 1,347 Tigers changed the replacement calculus. Losses on the battlefield are not simply matters of frontline casualties of machinery. They are a contest of attrition and replacement. If one side can field dozens of effective tanks daily, and the other side can only replace a handful, the statistical odds begin to favor the mass producer. Operational readiness rates reinforce this picture. In the reports that circulated among staff and planners, American units often reported availability figures above 85%, while some German formations struggled with readiness numbers in the 35–45% range. That gap is more than a statistic. It is the daily truth of whether armored formations can be committed, held in reserve, or withdrawn for repair. High availability means more tanks in action, more chances to seize fleeting opportunities, and less strain on recovery and depot systems. It bears repeating carefully. These numbers do not imply that one design was flawless and the other worthless. They say something narrower but vitally important about the sustained capacity to project armored power. A technically superior tank that is frequently broken or unsustainable in production loses whatever advantage it might have had in controlled comparisons. A simpler, robust, and widely produced vehicle that can be repaired quickly and kept in the fight day after day becomes in aggregate more potent. The captured Sherman became, in effect, a teacher. War Daddy 2 was not a charismatic general on a lectern. It was a collection of design choices that, when measured against the logistics of war, taught an unglamorous lesson. Working machines win. The lesson was not greeted with unanimous acceptance. Institutional habits, cultural pride and technical finesse, and the inertia of procurement and doctrine make change slow. But the evidence was hard to dismiss. It was present in the hum of the engine, in the clean beat of a weld, in the long life of gears that did not demand constant replacement, and in the small stabilizer that enabled quicker first shots. The strategic implications ripple outward. Mass production is not only about quantity, it is about designing each unit so it can be produced, maintained, and returned to service with minimal specialized effort. That means accessible service points, modular parts that can be swapped in the field, and tolerances that favor reliability over minute performance margins that can break under battlefield stress. It means tooling investments that allow many factories with modestly skilled labor to contribute, rather than a few workshops of highly specialized artisans who are easily disrupted by bombing or supply shortages. There is a human dimension to this industrial argument. Crews who could perform routine maintenance without waiting for depot help felt less helpless on the road. Recovery crews that spent less time hauling a tank 3 miles to the rear had more capacity to respond elsewhere. Frontline commanders who knew a percentage of their force would be up and ready to move the next morning could plan bolder movements. Conversely, technical brilliance that produced fragile machines imposed a constant psychological and operational tax. The discipline of conserving capabilities, the forced decisions to hold back assets lest they fail, and the slow attrition of availability that eventually choked offensive operations. Historical reflection must avoid simple moralism. The Germans were not foolish for valuing technical excellence. Allied engineers were not sanctimonious for valuing quantity and maintainability. Both sides gave different answers to the same problem. What War Daddy II and the Kummersdorf reports revealed was that in a war determined by attrition and mass mobilization, the answer rooted in industrial pragmatism had decisive advantages. The final image of the captured Sherman is quiet. It is not a monument. It is a tank sitting on a yard, dust still in its tracks, with engineers poring over plates and charts and generals writing their evaluations. To the casual eye, the hill climb had been a victory for the German design ideal. To the engineers and to those who measured war in months rather than moments, the Sherman was a more disruptive force, less glamorous on a single test, but more resilient in the reckoning that matters. That reckoning is simple to state and complex to accept. In the industrial contest of modern war, availability, maintainability, and the ability to produce at scale can be more decisive than marginal technical superiority. War Daddy II taught that lesson with metal and geometry and maintenance logs. It taught it by being a machine that could be fixed in the field, by showing transmission life measured in thousands rather than hundreds of miles, and by carrying a device that let crews get the first accurate shot faster. If you want to follow up on how production numbers and logistics decided armored warfare, watch the video about how industrial capacity shaped victory, and subscribe for more deep dives into the machines that made history.